If you have ever worked on a group project, you know the exact feeling of trying to keep track of everyone's supplies. The more people you add, the harder it gets to see the big picture. Imagine we write our inventory down like this. Ram has 20 books and 10 pens. Sita has 10 books and 5 pens. And Radha has 5 books and 7 pens. We can make this much easier to read. We'll arrange the students' names on the left and place our categories, books, and pens across the top. Translating messy, real-world data into a visual grid is the first step toward making complex information searchable and manageable. Once we understand the layout, we can remove the labels. When we wrap the remaining numbers in large square brackets, we have created a formal mathematical structure called a matrix. Every matrix has 2 directions. First, we read from left to right. These horizontal lines of data are called rows. In this example, we have 3 rows. Next, we read straight up and down. These vertical lines are called columns. Here, we have 2 columns. These dimensions give the matrix its order. We find it by stating the number of rows followed by the number of columns. Since we have 3 rows and 2 columns, this is a 3 by 2 matrix. Defining the order is a standard way to categorize matrices, allowing us to compare their sizes and see if they have enough room for the data we want to process. Matrices are grouped into different types based entirely on the shape of the grid they create. Isolating Ram's inventory into one horizontal line creates a row matrix. Isolating the 3 students' total book counts into a single vertical line forms a column matrix. When the number of rows matches the columns, the grid forms a perfect square, called a square matrix. Recognizing these basic shapes helps mathematicians understand the balance and boundaries of the data they're analyzing. Inside a square matrix, numbers running from top left to bottom right form the main diagonal. If these are the only numbers and everything else is 0, it's a diagonal matrix. If these diagonal numbers share the same value, it becomes a scalar matrix. These specific internal patterns act as mathematical shortcuts. By focusing on the diagonal, we can perform calculations on the important values while ignoring the zeros surrounding them. The most frequent pattern we see is when the diagonal numbers are all exactly 1. This is the identity matrix. In basic arithmetic, multiplying any number by 1 keeps that number the same. The identity matrix performs that exact same function for entire grids of data. At the other extreme, we have the 0 matrix, where every single entry is a 0. Just as the numbers 1 and 0 define the starting point for basic addition and multiplication, the identity and 0 matrices define how grids are preserved or canceled out in matrix math. Now you can look at a complex grid and immediately identify its rows, its columns, and its internal patterns. This organization creates a standardized, rigid roadmap that modern computers use to process millions of data entries simultaneously. Because the computer knows exactly where each piece of data sits in the grid, it can perform thousands of calculations in a single step. This is the same logic we used for our student inventory. We've simply scaled that organization up to handle larger sets of information. Matrices aren't intimidating math concepts. They are the connective tissue between human record keeping and digital computing power.